When transitioning a building designation from low-rise to high-rise, several electrical considerations beyond fire alarm codes come into play. These differences are crucial for ensuring safety, reliability, and code compliance in the electrical systems. Firstly, fire resistance becomes paramount. High-rise buildings necessitate the use of fire-rated cables and conduit throughout the entire structure. This is not merely a suggestion, but a requirement to maintain the integrity of the electrical system during a fire. The fire-rated materials prevent the spread of flames along electrical pathways, providing crucial time for evacuation and firefighting efforts. Secondly, emergency power systems are significantly more robust in high-rise buildings. Redundant systems, such as standby generators and uninterruptible power supplies, commonly referred to as UPS, are essential. These systems ensure that critical services like fire alarms, elevators, and emergency lighting remain operational during a power outage. The capacity and redundancy of these systems must meet stringent code requirements to guarantee uninterrupted power to life safety systems. Thirdly, exit lighting requirements are stricter for high-rise buildings. The number of exit signs, their visibility, and the duration for which emergency lighting must remain illuminated are all subject to specific codes. These codes aim to facilitate safe and orderly evacuation during emergencies, ensuring that occupants can easily locate and follow designated escape routes. Fourthly, smoke control systems may be required in high-rise buildings. These systems, which include smoke dampers and smoke exhaust fans, are designed to manage smoke movement within the building. By creating smoke-free zones and directing smoke away from escape routes, these systems enhance the safety of occupants during a fire. Fifthly, grounding and bonding systems must be extensive to ensure electrical safety throughout the high-rise structure. This involves grounding all electrical equipment, metal building components, and any lightning protection systems. Proper grounding and bonding minimize the risk of electrical shock and prevent the buildup of static electricity, protecting both people and equipment. Sixthly, overcurrent protection requirements can be more stringent, often involving the use of selective coordination. Selective coordination ensures that a fault on one circuit does not disrupt power to other critical circuits. This minimizes damage and reduces the risk of widespread outages, allowing essential systems to remain operational. Seventhly, voltage drop is a significant concern in high-rise buildings due to the long vertical runs of electrical cabling. Engineers must carefully calculate voltage drop and select appropriate wire sizes and routing to maintain acceptable voltage levels at all points in the building. Insufficient voltage can cause equipment malfunction and reduce the efficiency of electrical systems. Eighthly, communication systems in high-rise buildings are typically more complex, including intercoms, paging systems, and security cameras. These systems require additional wiring and coordination to ensure seamless communication throughout the building, particularly during emergencies. Ninthly, building automation systems are often employed to control heating, ventilation, and air conditioning, often abbreviated as HVAC, lighting, and other building functions. Integrating these systems requires additional wiring and careful coordination with other electrical systems to optimize energy efficiency and building performance. Tenthly, inspection and testing requirements for electrical systems are more rigorous in high-rise buildings. Regular inspections of fire alarm systems, emergency power systems, and electrical equipment are essential to identify and address potential problems before they lead to safety hazards or system failures. In more detail, the selection and installation of fire-rated cables and conduits is crucial. These materials are designed to withstand high temperatures for a specified period, preventing the spread of fire through electrical pathways. The fire rating of the cables and conduits must meet or exceed the requirements of the applicable building codes and standards. Emergency power systems must be sized to accommodate the essential loads in the building, including fire pumps, elevators, and emergency lighting. The systems must also be equipped with automatic transfer switches to ensure seamless transition to emergency power in the event of a utility outage. The capacity and reliability of the emergency power systems are critical for maintaining life safety during emergencies. Exit lighting must be strategically located to guide occupants to safety during a fire or other emergency. The exit signs must be clearly visible and illuminated at all times, and the emergency lighting must provide sufficient illumination to allow occupants to safely navigate the escape routes. The design and installation of exit lighting must comply with the applicable building codes and standards. Smoke control systems are designed to manage smoke movement within the building, preventing it from spreading to escape routes and other critical areas. The systems typically include smoke dampers, smoke exhaust fans, and a control system that automatically activates the systems in the event of a fire. The design and operation of smoke control systems must be carefully coordinated to ensure their effectiveness. Grounding and bonding systems must be installed to minimize the risk of electrical shock and prevent the buildup of static electricity. The systems must comply with the applicable electrical codes and standards, and they must be regularly inspected and tested to ensure their effectiveness. Selective coordination of overcurrent protection devices is essential for minimizing the impact of faults on the electrical system. Selective coordination ensures that the overcurrent protection device closest to the fault trips first, isolating the fault and preventing it from spreading to other circuits. This minimizes damage and reduces the risk of widespread outages. Voltage drop calculations must be performed to ensure that the voltage at all points in the building is within acceptable limits. The calculations must take into account the length of the cable runs, the size of the conductors, and the load current. The wire sizes and routing must be carefully selected to minimize voltage drop and ensure that equipment operates properly. Communication systems must be designed to provide reliable communication throughout the building, particularly during emergencies. The systems must be equipped with backup power and be designed to withstand adverse conditions. The design and installation of communication systems must comply with the applicable codes and standards. Building automation systems can be used to optimize energy efficiency and improve building performance. The systems can control lighting, heating, ventilation, and air conditioning and other building functions, and they can be integrated with other building systems to provide a comprehensive view of building operations. Regular inspections and testing of electrical systems are essential for ensuring their safety and reliability. The inspections and testing must be performed by qualified personnel and must comply with the applicable codes and standards. In the design and construction of a high-rise building, adherence to these electrical considerations is paramount. These measures ensure the safety of occupants, the reliability of electrical systems, and compliance with all applicable codes and regulations. Failure to address these considerations can have serious consequences, including fire hazards, electrical shock risks, and system failures. Therefore, it is essential that engineers and contractors involved in the design and construction of high-rise buildings have a thorough understanding of these electrical requirements. The NEC, or National Electrical Code, provides detailed guidance on the installation of electrical systems in buildings, including high-rise buildings. Article 518 addresses places of assembly, which may be relevant for hotels with large meeting rooms or ballrooms. Article 620 covers elevators, dumbwaiters, escalators, moving walks, wheelchair lifts, and stairway chair lifts. Article 700 pertains to emergency systems, which are critical for high-rise buildings. Article 701 addresses legally required standby systems, which may be required for certain types of occupancies. Article 702 covers optional standby systems, which provide power for non-essential loads during a power outage. In addition to the NEC, local building codes and regulations may also impose specific requirements for electrical systems in high-rise buildings. It is essential to consult with local authorities and qualified professionals to ensure compliance with all applicable codes and regulations. Moreover, consider the specific requirements of the hotel occupancy. Hotels have unique electrical demands due to guest rooms, commercial kitchens, laundry facilities, and other amenities. The electrical system must be designed to accommodate these demands while also providing adequate safety and reliability. For example, ground fault circuit interrupters, also known as GFCIs, are required in bathrooms, kitchens, and other wet locations to protect against electrical shock. Surge protection devices, often called SPD, are recommended to protect sensitive electronic equipment from voltage surges. Energy-efficient lighting and controls can help reduce energy consumption and lower operating costs. Furthermore, consider the future needs of the building. The electrical system should be designed with sufficient capacity to accommodate future growth and changes in technology. This may involve installing larger conduits, providing spare capacity in panel boards, and using flexible wiring systems. Regular maintenance and testing are essential for ensuring the long-term reliability of the electrical system. A qualified electrical contractor should be engaged to perform regular inspections, testing, and maintenance. This will help identify and address potential problems before they lead to safety hazards or system failures. In conclusion, transitioning a building designation from low-rise to high-rise involves significant electrical considerations beyond fire alarm codes. These considerations include fire resistance, emergency power, exit lighting, smoke control, grounding and bonding, overcurrent protection, voltage drop, communication systems, building automation, and inspection and testing. Adherence to these requirements is essential for ensuring the safety of occupants, the reliability of electrical systems, and compliance with all applicable codes and regulations. The NEC provides detailed guidance on the installation of electrical systems in buildings, including high-rise buildings. Local building codes and regulations may also impose specific requirements. It is essential to consult with local authorities and qualified professionals to ensure compliance with all applicable codes and regulations. Always remember that safety and adherence to local codes are of utmost importance in these projects. Electrical engineering demands a deep understanding of these regulations and best practices to ensure the well-being of all occupants and the integrity of the building's systems.